In the previous lecture, we have discussed a very important law which is called Bragg's law. You know, Bragg's law is actually a basic law for X-ray diffraction, and it has so many applications in discussing the crystal structure. So after knowing Bragg's law, now we will see the application part of this law. Okay, and in this first lecture on application of Bragg's law, we are going to see how this law is used to determine the wavelength of X-rays. Actually, Bragg himself determined wavelength of X-ray using his law. Okay, so this is the first and the simplest application of Bragg's law. And after this application, we will see another applications in which we will discuss how this law can be used to discuss the crystal structure. Okay, so let us start uh, from very beginning. I am just repeating the fact which you have discussed in earlier lectures. Just a revision. I am giving you what is this Bragg's law, and then we will see how this law is used in determination of wavelength of X-rays. You have already seen in earlier lecture that mathematically we express Bragg's law in this form: 2d sine theta equal to n lambda. This is a very simple law. You know, when X-rays beam are incident on a crystal, they get reflected or diffracted. In fact, here in terms for the term diffraction, we use the term Bragg's reflection. But when you say Bragg's reflection, you know that is simply diffraction of X-rays. And for the condition of maximum intensity of reflected beams of X-rays, Bragg have obtained a condition, and mathematically that condition is given by 2d sine theta equal to n lambda, and this very equation is known as Bragg's equation or Bragg's law. You know, you have already discussed this law in very detail in your previous lecture. Okay, and you also know what the different quantities in this equations refer. You know, this d is what? This is interplanar spacing, or this you can say that this is the interplanar distance between the two successive parallel planes of the crystal. And theta, this is glancing angle, that is the angle made by the incident X-ray beam with the crystal plane. Okay, and lambda is wavelength of X-ray, and n actually refers here the order of maxima or order of diffraction maxima, you can say, or simply it is also said that it is order of diffraction. Okay, but when you say diffraction, that means diffraction maxima. And you have seen earlier that actually the zeroth order diffraction maxima is not observed in experiment, so n cannot be equal to 0 in this case. So n is equal to 1, 2, 3 and so on. When you say n equal to 1, that means first order diffraction maxima n equal to 2 refers, second order diffraction maxima n equal to 3 refers, third order diffraction maxima and so on. Okay, and from this equation you can easily see that using this very equation we can determine the wavelength of X-ray, because from this equation you can see this lambda, which is wavelength of X-ray, that will be what? That will be simply 2d sine theta divided by n. So it is clear that if we know the interplanar spacing of a crystal, the glancing angle theta and the order of maxima, then using this formula it is very easy to calculate the wavelength of X-ray. So using his law, Bragg's actually determined the wavelength of X-ray. by using a apparatus which is commonly known as Bragg's spectrometer. Okay. So first of all, we will see the experimental detail in short, and after that we will see how we can calculate uh, wavelength lambda of X-ray. Actually, this experiment was originally performed by Bragg himself, as I have told you earlier. Okay, and so that the apparatus used by him is also called Bragg's spectrometer. Okay, so now let us see the first of all the experimental arrangement, and then we will see how the wavelength will be calculated, okay, by this experiment. And for this I have shown in this figure the schematic diagram. When you say schematic diagram, that means I have not shown all the parts of the apparatus, but only those parts of the apparatus have been shown in this figure, which is essential to know the experimental detail. Okay, so this is just the important parts of, or you can say essential parts of Bragg's X-ray spectrometer shown in this figure. Okay, you can see here I have shown, I have written that this dot represents the source of X-ray. When you when you say source of X-ray, you know X-rays or Rontgen rays, you also call it, are produced from anti-cathode. So from anti-cathode, X-rays are produced. And in this experiment, we need a collimated beam of X-rays. So to get collimated beam or a pencil-like beam, the X-rays obtained from the anti-cathode are passed through several slits. I have shown in this figure two slits, S1 and S2. And after passing through these two slits, X-ray beam are highly collimated. Okay, and that collimated beam are incident on a crystal. I have shown here in this figure this C. You can see this rod-like structure. This is actually the crystal on which these collimated beam of X-rays are incident. And I have shown that these rays are incident at an angle theta, which is actually the glancing angle. Okay. Actually, this crystal C is placed on a circular table, which is also called the turntable, because this circular table rotates about a vertical axis. So this is also called turntable. Okay. So you can say that the crystal on which the collimated X-ray beam is incident has been placed on a circular table or a turntable which is capable to rotate about a vertical axis. Okay. And how much this table is rotated, that can be measured by a vernier scale, which is shown here by V1. So this vernier V1 is used to measure the rotation of the table. Okay, and there is also a circular scale. So with the help of the circular scale and the vernier scale V1, the rotation of the turntable is measured. Okay, I think you are getting the things. Now, when the X-ray beam is incident on the crystal C, it get reflected, and you can see I have marked this reflected ray here by this arrow sign. You can see in the figure. And this reflected rays passed through the slit S3 and enters the ionization chamber I, where you can see here I have marked by I. This is ionization chamber. Actually, in the ionization chamber, a gas, particularly methyl iodide, is filled. And when X-rays incident, when this reflected beam of X-ray enters into the ionization chamber, the molecules of the methyl iodide gets ionized, and so ionization current is produced, and that ionization current is measured with the help of this electrometer E, which I have shown in this figure. Okay. Actually, this ionization chamber is mounted on the axis, and its position is determined by the second vernier V2. You can see in this figure. Okay. Actually, in this experiment, we measure the ionization current for different value of theta. In fact, in using this apparatus, the crystal is placed in such a position that theta is equal to 0. First of all, the crystal is placed in this manner so that theta is equal to 0. And the ionization chamber is then adjusted to receive the X-ray. Okay. The angle theta increases by rotating the crystal. When you will rotate the crystal, then this theta will increase. Okay. This theta will increase from 0. Okay. And each time the ionization current is measured, it means for different value of theta, we measure the ionization current. Okay. So, for let us say for angle when theta is theta 1, ionization current is I1. When theta is theta 2, ionization current is I2. When theta is theta 3, ionization current is I3. It means for different value of theta, we measure the corresponding value of ionization current. Okay. And after that, we plot a graph of the ionization current in against of theta. Okay. Actually, when we plot a graph of the ionization current versus theta, then it is seen that the ionization current at first falls as theta increases. When theta will increase, then ionization current falls or decreases firstly. But for certain value of theta, it is found that the curve abruptly rises. It rises. Okay. And we get a maximum. Okay. Actually, this maxima corresponds to the direction of X-ray spectrum. The X-ray spectrum, when a maxima will get is obtained, that corresponds to the diffraction maxima. It means when the intensity of the diffracted interfering beams will be maximum, then ionization current will be maximum. So here, I actually is when I max, it means when ionization current is maximum, that means intensity is maximum. So the measuring quantity is ionization current, but that is equivalent to intensity. Okay. So from that very graph, you can measure what will be the value of theta for different order of maxima. I am just showing you the graphical plot of ionization current versus theta for two wavelengths, let us say lambda 1 and lambda 2. We will show. Actually, for your convenience, all those things which I have just discussed, which we have just explained, I have written for your convenience. So, this I have written because of your convenience. You can note down these facts in your notebook, and that will be a good note for your examination purpose, particularly for your university examination purpose or the examination like civil services, where you have to write down the experimental detail too. Okay. So I have written all those things. Okay. I am not repeating those things because I have already explained it. So if you want to note these things in your notebook, you can pause the video and you can note down these facts in your notebook. Okay. So now let us see the graphical plot which I have not shown the graphical plot here, but just I am showing it to you. You can see in the last I am showing the graphical plot because in this lecture I have not plotted that graph, but I am plotting it here. You can see. Let us see on this y-axis. I am just noting the ionization current, and on this horizontal axis we will note theta. Okay, and you will see that when I will be plotted in against of theta, the curve will be like this. Actually here I have plotted this graph for two wavelengths, let us say lambda 1 and lambda 2, and you can see the points which are just marked by me in this figure, that corresponds to the maxima. This is Q3 and this is P3. Okay. And if you consider that these maxima Q1, Q2, Q3, these are actually the first order, second order, third order maxima. If for wavelength lambda 1, then this P1, P2, P3, these are the maxima for the second wavelength, let us say lambda 2. Okay. For the two wavelengths lambda 1 and lambda 2, I have shown the graphical plot of ionization current in against of theta. Actually, it is seen that we can measure from this figure what will be the value of theta for the maximum value of ionization current. Let us consider when we talk about the maximum P1, P2, P3 corresponding to the wavelength lambda 2, let us say, then for the first order maxima, that is when n is equal to 1, we get the maximum value P1, and let us say this for this the value of theta is theta 1, and similarly for the another maxima the value of theta is theta 2, and for the third maxima it is theta 3. We consider. So from this graph we can calculate the value of theta for which intensity is maximum. Although in experiment we see that ionization current is maximum, but when you say ionization current is maximum, that means intensity of diffracted beam is maximum. So for first order diffraction maxima, you can measure the value of theta from this graph. Okay, it means for which value of theta we get the first order maxima, we can easily measure from this graph. So the value of theta corresponding to which we have different order of maxima, that is measured by this graph. In fact, it is clear that the intensity of a line corresponding to a certain value of wavelength decreases, whereas the separation between the line corresponding to two near wavelengths increases with the order of a spectrum, as you can see in this figure. Okay, so from this figure you can measure the value of theta once corresponding to the given order of maxima. Okay, Once you have obtained the value of theta for the uh, given order of maxima, then using Bragg's equation, we can easily find what will be the wavelength. As you can see here, that according to Bragg's law, you know 2d sine theta equal to n lambda. Okay, and so from here lambda by d will be equal to 2 sine theta by n. Okay. Now, as I have told you, for a particular wavelength, for different order of maxima, we have different value of theta, which is measured from that graphical plot. So, we will substitute the value of theta equal to theta 1, then we will for n equal to 1, and then we will obtain what is lambda by d. Okay, again we will put theta equal to theta 2 for n equal to 2, and then again find the value of lambda by d from this equation. D is also constant. Lambda will have different value because in one reading you never get the accurate value. So always in physics we obtain the average value. Okay. So in this way, from this equation 1, substituting the value of theta for a given value of n, we obtain the different value of lambda by d, and then we will obtain the average value of lambda by d. So if you consider that lambda by d average is equal to x, then what will be the average value of lambda? Lambda average will be x into d. In this way, as d for a given crystal is constant and that can be measured, so substituting the value of d, that is interplanar spacing for the crystal used in your experiment, and substituting the value of x which you have obtained here, you can easily find what will be the average wavelength. Average, why average is found? You know, in experiment in physics, we always find the average value because in one reading you never get the accurate value. That's why we take at least 3 order of maxima, and corresponding to the first, second, third order, we will obtain lambda by d, and after that we will obtain the average value of lambda. That will be the wavelength of X-ray used. Okay. But this equation refers that you can calculate lambda average only when you know the interplanar spacing d. Okay, but how we can obtain d? For this, I am just taking a simple example of a crystal, sodium chloride. You know, sodium chloride is a simple cubic crystal, simple cubic, or you can say primitive, and so its unit cell is just a cube. Okay, and side of the cube in this case will be equal to d. Okay, and you know, in sodium chloride crystal, actually the sodium ion, that is Na plus, and chlorine ion, both are alternately arranged at the corners of this cube. Okay, so from the study of action of X-ray on this crystal, we found that this crystal is cubic, and sodium ion and chlorine ion are arranged alternately at the corners of the elementary cube. Okay, actually every elementary cube has 8 ions at its corners. Okay, 4 of sodium ion and 4 of chlorine. Okay, actually every cube is surrounded on all sides by other such cubes. Okay, and thus each ion of sodium chloride is shared between two cubes. Okay, it means when you talk about this Cl minus, this will be shared between two cubes. Na plus, that will be also shared between two cubes. And so each elementary cube contains only half of a molecule of sodium chloride. So if you want to know the mass of this elementary cube, you should think that the only the half of the mass of this cube is associated with it, because each ion is shared between two elementary cubes. Okay. Now, what will be the mass of this ion, this cube? How we can find? If you consider that m is the molecular weight of this sodium chloride molecule, then you know when we write molecular weight in gram, that represents the mass of 1 mole of the substance. So if m is the molecular weight, that means m gram will be equivalent to what? 1 mole. And 1 mole, you know, is equivalent to Na molecules. Na is Avogadro number. Okay. Na is Avogadro number. Okay. So you can say that mass of Na molecules is equal to m gram. So mass of one molecule will be what? That will be m by Na. So whenever we divide the molecular weight by Avogadro number, we get the mass of one molecule. Okay. But here, since half of the mass of the molecule is contained in this cube, because each ion is shared between two, so actually in this case, mass of this elementary cube will be not m by Na, but it will be just half of it. And therefore, I have written here, you can see m is equal to m divided by 2Na. Okay. So I have written here, you can see, thus each ion of NaCl is shared between two cubes, and each elementary cube contains half a molecule of it. That's why the mass of the molecule will be simply m divided by 2Na, not m by Na. Okay. M, this is molecular weight, which is equal to what? NaCl, you know, atomic weight of Na is 23 and that of Cl is 35.5. So the molecular weight of this NaCl is 58.5. Okay. And Na, which is Avogadro number, that is equal to 6.023 into 10 to the power 23. So substituting the value of m and Na, you can get what will be the mass of this cube. Okay. So mass of this cube, you can see it, this will be this much. This is 58.5 divided by 2 into 6.023 into 10 to the power 23 gram. Okay. Now, our aim is to find D, and you have seen that the side length of each side length of this cube is equal to D. So the volume of the elementary cube V will be equal to D cube. Okay. Now density of NaCl is already known. It is a standard data. Actually density of NaCl, that is sodium chloride, rho, is known. It is a standard data. This is 2.17 gram per cm cube, or you can say cc. Okay. So as we know density of sodium chloride, so from the relation between density and mass and volume, you can easily find what will be the value of D. You know, density of a material is m divided by V, mass divided by volume. And so V will be m by rho. Okay. But V is equal to D cube. So D cube is equal to m we will substitute the value of m from here. That will be 58.5 divided by 2 into 6.023 into 10 to the power 23 into rho. Rho is equal to 2.17 gram per cm cube. Okay. So D will be equal to cube root of this much. And when you will simplify it, after simplification, it is found that D is equal to this much. This is 2.82 into 10 to the power minus 8 centimeter. So this is the interplanar separation in, or you can say lattice constant in for the sodium chloride crystal. Okay. Now in experiment it is found that the first order Bragg's reflection, that is for n equal to 1, in case of sodium chloride crystal, glancing angle is found 11.4 degree. This is a experimental result. I have not calculated it, but it is found in experiment. If you will use in this experiment the crystal of sodium chloride, then it is found that the first order maxima occurs for theta equal to 11.4 degree. Okay. So from Bragg's law, you can see 2d sine theta equal to n lambda. But when n is equal to 1, then theta is equal to 11.4 degree. Okay. So you can substitute now all these values in this equation. 2d, you have seen that d is equal to 2.82 into 10 to the power minus 8 centimeter. Theta for first order maxima is found 11.4 degree. So sine theta is replaced by sine 11.4 degree, and n lambda, n is equal to 1 lambda. So when we will substitute the value of sine 11.4 degree, 11.4 degree is not a standard value. From the sine table you can substitute its value, and after simplification you will get that lambda is equal to this much. This is 1.1 into 10 to the power minus 8 centimeter. Or in other words, you can say this is 1.1 angstrom. Okay. So in this way, you can find the lattice constant D, and once you know the lattice constant using this Bragg's equation, you can easily find what will be actually the value of lambda. If this theta is known, how theta will be measured? As I have shown in this figure, that for first order maxima, we measure the glancing angle from this graph. This theta is measured from the graph, and it is found in case of NaCl crystal that for first order maxima, this theta is equal to 11.4 degree. So in this way, for different order, theta will be measured, and for different theta we will measure for different order of maxima the value of lambda, and after that the average value of all those lambda will be obtained. For example, in this figure I have shown three maxima, that is first maxima, second maxima, and third maxima. If you calculate lambda for the first order maxima, it is suppose this is lambda dash, for second order lambda double dash, for third order this is lambda triple dash. Then actual value of lambda will be average of all these, that will be lambda plus lambda double plus lambda triple plus divided by 3. And in this way we obtain the average value of wavelength of X-ray. I think you have clearly understand the experiment, how we can obtain or how we can measure the wavelength of X-ray using Bragg's law. This is a very important application, or the preliminary application of Bragg's law. Now in forthcoming lecture we will see how this Bragg's law is utilized in discussing the crystal structure or in determination of crystal structure. Okay, thank you very much.